The night of January 30th, 1943, 10,000 feet above the North Sea, Flight Lieutenant Peter Davies pressed his gloved hand against the frosted plexiglass of his Sterling bomber's cockpit. Below him, nothing but darkness. Around him, 6 other Pathfinder aircraft carrying 13 crews into German airspace with orders that seemed torn from science fiction. Navigate to Hamburg through 10,000 feet of solid cloud cover. Mark the target with incendiaries. Guide 100 Lancasters to bomb a city they would never actually see. Davies had flown 23 missions over Germany. Every one of them followed the same grim mathematics. On clear nights, German searchlights caught you. On cloudy nights, you bombed blind, hoping your dead reckoning calculations placed your payload somewhere near the target instead of miles into open countryside. The WWII report had revealed the devastating truth. Only 1 bomb in 20 landed within 5 miles of its intended target. Half of Bomber Command's ordnance fell on empty farmland. Tonight would be different. Mounted in Sterling bombers, belly turret position, a device so revolutionary that crews received their briefings only hours before takeoff. H2S, Home Sweet Home. The first airborne ground scanning radar system ever deployed in combat. Davies glanced back toward the cramped space where Navigator Flight Sergeant Thomas McKenna hunched over a green cathode ray tube displaying electromagnetic ghosts of the terrain 3 miles beneath their aircraft. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. McKenna had attended exactly 1 training session on H2S operation. 40 minutes of instruction on interpreting radar returns that distinguished water from land, cities from countryside, based solely on differences in reflected electromagnetic radiation. The technology operated at 9.1 centimeter wavelength, transmitting energy downward through a rotating antenna housed in the aerodynamic radome that replaced the bomber's standard ventral gun turret. Return signals appeared on the plan position indicator display as varying shades of contrast. Water returned weak signals, appearing dark. Built-up urban areas with concrete and brick returned strong signals, appearing bright. The concept seemed impossible by every measure of operational reality. German night fighters prowled invisibly through the same darkness. Flak batteries fired from positions invisible beneath cloud layers. The bomber stream navigated by dead reckoning, celestial navigation when stars were visible, or radio navigation aids like G that German jamming increasingly rendered useless. G's range limitation meant it functioned reliably only within 350 kilometers of its British transmitter stations. Beyond that distance, bombers flew using compass headings, airspeed calculations, and prayers. Hamburg lay beyond G's effective range. The target required 600 kilometers of navigation across open water and occupied territory, where a 5-degree heading error meant missing the city entirely. Previous raids on Hamburg had achieved minimal results. Bomber Command planners estimated that fewer than 30% of aircraft claiming to have bombed Hamburg actually dropped their loads anywhere near the target perimeter. Davies understood the stakes without comprehending the science. RAF Bomber Command was losing the mathematics of attrition warfare. British factories produced bombers faster than German defences destroyed them, but crew replacement rates couldn't match casualty statistics. 4% loss rates per mission meant trained air crews disappeared faster than training schools graduated replacements. At current attrition levels, Bomber Command would exhaust qualified personnel before achieving decisive strategic impact against German industrial capacity. The H2S development team had worked under conditions approaching desperation. In January 1942, scientists at the Telecommunications Research Establishment discovered that the cavity magnetron, Britain's most closely guarded technological secret, produced radar returns that varied dramatically based on target composition. Water, open land, and urban areas each generated distinctive electromagnetic signatures on radar screens. TRE physicist Bernard Lovell received orders to transform that laboratory observation into operational equipment within months. The technical challenges seemed insurmountable. Standard radar systems weighed hundreds of pounds and required stable mounting platforms. Lovell needed to create a complete radar installation compact enough to fit inside a bomber's belly turret, rugged enough to survive combat conditions, and simple enough for navigators to operate while managing their dozen other responsibilities during bombing runs. By March 19, 1942, Lovell's team had produced a prototype system installed in a Halifax bomber designated V9977. Test flights over English countryside demonstrated the system's potential. Cities appeared as bright concentrations on the display. Rivers and coastlines showed clear contrast between land and water returns. The radar could detect coastal features at ranges exceeding 50 miles, providing navigation reference points far beyond visual or radio navigation aid capabilities. The breakthrough carried terrible costs. On June 7, 1942, Halifax V9977 departed Herne Airport carrying Lovell's H2S development team for a demonstration flight intended to showcase the system to manufacturing engineers from EMI. 23 minutes into the flight, an engine fire developed. The pilot attempted emergency landing procedures, but the aircraft crashed near Welsh Bicknor, killing all 11 aboard. The crash destroyed the only failed, working H2S prototype. More devastating, it killed key members of the development team, including Alan Blumlein, a brilliant electronics engineer whose expertise in high-frequency systems had proved irreplaceable. Lovell would later write that he remained haunted by memories of colleagues lifeless under sheets near the charred wreckage of a bomber he had flown in unconcerned the previous evening. Winston Churchill's response demonstrated the system's perceived strategic importance. Despite the catastrophic setback, the Prime Minister personally ordered production of 200 H2S sets by October 19, 1942. When Lovell protested that such a deadline was technically impossible, Churchill remained unmoved. Bomber Command required H2S to continue operations. The current loss rates were unsustainable. British industrial capacity meant nothing if bomber crews died over Germany before destroying targets that justified their sacrifice. Production fell behind schedule immediately. The H2S system required miniaturized components that had never been mass-produced. The cavity magnetron represented cutting-edge microwave technology. The rotating antenna mechanism demanded precision manufacturing. The cathode ray tube display needed specialized construction. By January 1, 1943, only 24 sets had been completed, 12 installed in Stirling bombers, 12 in Halifax aircraft. Those 24 sets represented Britain's entire operational inventory of airborne ground scanning radar. They would equip Pathfinder squadrons, elite units responsible for locating and marking targets for the main bomber force. Pathfinder doctrine had evolved throughout 1942 as Bomber Command struggled with navigation accuracy. Specialized crews flying ahead of the main formation would identify targets using the best available navigation aids, then mark aiming points with colored flares and incendiary bombs. The following bomber stream would attack the marked areas, theoretically concentrating damage on actual military and industrial targets rather than dispersing bombs across countryside. H2S promised to transform Pathfinder effectiveness by eliminating dependence on visual target identification. Navigators could locate cities through solid overcast, identify distinctive geographical features like rivers and harbors, mark targets with unprecedented accuracy regardless of weather conditions or German defensive measures. The risks were substantial and widely debated. H2S transmission required revealing Britain's cavity magnetron technology to German engineers. If an equipped bomber was shot down over enemy territory and the wreckage recovered intact, German scientists would immediately recognize the revolutionary nature of British microwave technology. Intelligence estimates suggested Germany lagged years behind Britain in cavity magnetron development. Revealing the device's existence might accelerate German radar programs by providing a functional example to reverse engineer. Air Ministry officials argued for restrictions on H2S deployment. Use the system only over water, where crashed aircraft would sink beyond enemy recovery. Prohibit operations over German territory, where wreckage could be examined. Accept continued bombing inaccuracy, rather than risk compromising Britain's most valuable technological advantage. Bomber Harris rejected such limitations with characteristic bluntness. His air crews faced real flak, real fighters, real weather. German technological advantages meant British bombers died at unsustainable rates. H2S offered potential salvation through improved navigation and target finding. The theoretical risk of technology compromise mattered less than the demonstrated reality of current casualty statistics. Churchill agreed. British survival depended on maintaining strategic bombing pressure against German industrial capacity. Current bombing accuracy rendered the campaign nearly worthless. Half of all bombs fell on open countryside. Even on missions where bombers reached their intended target cities, ordnance scattered across residential areas miles from actual military installations. H2S represented the only available solution to navigation problems that threatened to make British bombing operations strategically irrelevant, despite enormous resource expenditure. On January 28, 1943, Pathfinder Squadron commanders received their operational briefing. Hamburg would be attacked on the night of January 30th using H2S for primary navigation and target marking. 13 aircraft would carry the experimental equipment. 6 must successfully mark the target to ensure the following Lancaster force could identify and bomb the aiming point. Flight Sergeant McKenna attended the navigator's technical briefing in a cold hangar at RAF base, receiving his first comprehensive explanation of the system he would operate in combat 48 hours later. The instructor, a TRE scientist who had never flown combat missions, explained H2S operation with clinical precision. The display showed a circular representation of terrain within selectable range settings, 10-mile range for precise target identification during bombing runs, 50-mile range for long-range navigation using coastal features. The antenna rotated continuously, scanning 360 degrees around the aircraft. Fresh radar returns painted the display every rotation, creating a real-time map of the ground beneath their bomber. Water appeared dark because liquid surfaces absorbed and scattered electromagnetic energy rather than reflecting it back toward the aircraft. Urban areas with metal roofs, concrete buildings, and paved streets returned strong signals that appeared bright on the display. Open countryside with vegetation and scattered structures showed moderate contrast. The navigator's responsibility involved interpreting these electromagnetic variations to identify cities, coastlines, rivers, harbours, and other landmarks useful for navigation and target identification. McKenna listened with growing skepticism. The instructor had never attempted to interpret radar returns while flying through flak concentrations at night in freezing temperatures, with German fighters hunting the bomber stream. The theoretical elegance of electromagnetic navigation meant nothing if the system proved too complex for operational use under combat stress. The test began over the North Sea shortly after midnight on January 31, 1943. McKenna activated the H2S system and watched the cathode ray tube illuminate with its ghostly green glow. At first, nothing but electronic noise cluttered the display. Then, gradually, patterns emerged. The solid darkness of water below, a bright return ahead that steadily grew stronger as they approached the German coastline. Hamburg's location at the mouth of the Elbe River created perfect conditions for H2S identification. The sharp contrast between water and land appeared unmistakable on the radar display. McKenna could distinguish the river's path inland, the harbour installations, the dense urban centre that showed as the brightest concentration of radar returns. For the first time in 23 missions, he could navigate to a target he couldn't see with his eyes, but could track electronically through any weather, any darkness, any German defensive measure that didn't involve physically destroying his aircraft. Davies received the confirmation he'd been waiting for. McKenna had positive identification. They were exactly on course. Hamburg lay 12 minutes ahead. The 6 Pathfinder aircraft carrying functional H2S systems began their marking runs at 5 minutes before 1 in the morning. Yellow target indicators and flares fell through the darkness toward a city hidden beneath solid overcast. The following Lancaster. Force, 100 aircraft carrying high explosive and incendiary bombs, would bomb on those markers, trusting that Pathfinder navigation had placed them over actual German targets rather than empty countryside. The implications of that night's operation extended far beyond a single raid on Hamburg. For the first time in the war, British bombers had demonstrated the capability to bomb through complete cloud cover using self-contained electronic navigation that required no ground-based transmitters, no visual references, no celestial navigation, and no dependence on systems vulnerable to German jamming. 200 miles southeast, in a signals intelligence facility near Hamburg, Lieutenant Werner Fischer monitored German radar networks searching for the approaching British formation. The Freya early warning stations had detected the bomber stream while it was still over the North Sea. Regional air defense commanders had scrambled Messerschmitt night fighters and alerted flak batteries throughout northwestern Germany. Fischer's responsibility involved coordinating defensive response based on raid composition and probable targets. Tonight's raid followed standard British procedures: large formation approaching from the northwest. Speed and altitude characteristics consistent with four-engine heavy bombers, estimated strength between 150 and 200 aircraft based on Freya returns. But Fischer noticed something unusual in the electromagnetic signature. Several aircraft in the leading elements were transmitting radio frequency energy at wavelengths his monitoring equipment had never detected from British bombers before. The transmissions occurred at approximately 3 GHz frequency, corresponding to 9 to 10 centimeter wavelengths. That frequency range exceeded German radar capabilities. Reich air defense systems operated at lower frequencies with longer wavelengths because German engineers had never successfully miniaturized the components necessary for centimetric radar operation. Fischer documented the unusual emissions in his log, noting that several lead aircraft appeared to be carrying some form of previously unknown British radar equipment. The significance wouldn't become clear for 2 more days. On February 2, 1943, during a raid on Cologne, a Sterling Pathfinder aircraft was shot down over Rotterdam by a German night fighter crew. The wreckage was recovered largely intact. Telefunken engineers examining the debris discovered a partially damaged but recognizable radar installation unlike anything they had previously encountered. The device, which German technicians would designate the Rotterdam Gerät, contained a cavity magnetron operating at centimetric wavelengths. German scientists examining the equipment experienced professional shock. They had assumed British radar technology lagged behind German developments. The cavity magnetron proved that assumption catastrophically wrong. British engineers had achieved microwave radar miniaturization that German research teams had deemed impossible. Within weeks, Telefunken had reconstructed the H2S system sufficiently to demonstrate its capabilities. When they activated the repaired equipment and pointed it toward Berlin, a detailed radar map of the German capital appeared on the display, showing streets, parks, rivers, and major buildings with unprecedented clarity. Hermann Göring, viewing the demonstration, reportedly responded with fury. British bombers could now navigate to German cities using radar systems that German defences couldn't jam and German engineers couldn't replicate. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The German response combined technological development with strategic denial. Telefunken received orders to develop radar warning receivers capable of detecting H2S transmissions. If German night fighters could home in on British radar emissions, the system that was supposed to protect bomber crews might instead betray their positions to enemy interceptors. By September 1943, German engineers had produced the FUG 350 Naxos radar detector. The system could detect H2S transmissions at ranges exceeding 35 kilometers, allowing night fighters to locate the general position of the bomber stream without achieving sufficient precision to guide interceptions against individual aircraft. Naxos provided warning and general direction, not the pinpoint accuracy needed for night fighting. Intelligence about Naxos reached Britain by spring 1944, triggering fierce debate about whether to continue H2S operations. Some officials argued that the system's electromagnetic emissions were marking British bombers for German fighters, increasing rather than decreasing casualties. Statistical analysis eventually revealed that bomber losses had actually decreased after H2S deployment, despite the introduction of Naxos. The improved navigation and target-finding capability provided by radar outweighed whatever tactical advantage German fighters gained from detecting transmissions. By July 1943, H2S had been fitted to Lancaster bombers, transforming them into the backbone of Bomber Command's strategic campaign. On the night of July 24th, 791 RAF bombers departed English airfields carrying 92 million strips of aluminum chaff designated window and carrying H2S equipment that would guide them through solid overcast to Hamburg for Operation Gomorrah. The raid demonstrated H2S at peak effectiveness. Pathfinders marked the target with exceptional accuracy. The main force concentrated their bombing on marked areas with unprecedented precision. The combination of window defeating German radar defenses and H2S enabling accurate navigation through complete cloud cover created conditions where British bombers could attack German cities almost unopposed. Hamburg burned. 45,000 civilians died in the firestorm that developed during the July 27th attack. The destruction validated every prediction made by H2S advocates. For the first time, Bomber Command had achieved concentrated, devastating attack against a major German industrial center, despite weather conditions that would have made such operations impossible using conventional navigation methods. But Hamburg's geography had favored H2S operation. The coastal city, with its clear contrast between water and land, its distinctive harbour, its compact urban centre, all appeared unmistakable on radar displays. Berlin would present entirely different challenges. The German capital lay deep inside enemy territory, beyond the range of British radio navigation aids. The city stretched across hundreds of square kilometres, so large that it filled the entire H2S display on normal range settings. The distinctive geographical features that made Hamburg easy to identify didn't exist in Berlin. The city's lakes and rivers appeared as small details lost in the massive radar return from endless urban development. Air Chief Marshal Arthur Harris believed Berlin represented the decisive target. "We can wreck Berlin from end to end if the USAAF come in with us. It will cost us between 400 and 500 aircraft. It will cost Germany the war." By November 1943, Harris commanded over 800 serviceable heavy bombers equipped with H2S. The Americans declined to participate, still recovering from devastating losses over Schweinfurt. Bomber Command would attack Berlin alone, relying on H2S to guide them through winter weather that kept the city perpetually shrouded in cloud. The Battle of Berlin began on the night of November 18, 1943. 440 Lancasters and 4 Mosquitoes attacked the German capital through 10,000-foot overcast. The city was under cloud, and the damage was not severe. Pathfinder marking had been scattered. H2S operators struggled to distinguish specific aiming points in the massive radar return that Berlin generated. The raids continued through winter, November 22nd, December 2nd, January 2nd, January 20th, February 15th. 16 major attacks between November 1943 and March 1944. Each raid followed similar patterns. Bomber Command assembled formations of 600 to 800 aircraft. They flew to Berlin through darkness and clouds. Pathfinders using H2S attempted to mark industrial and government districts. The main force bombed the markers, hoping their ordnance struck German military capacity rather than residential areas. The results proved mixed at best. H2S performed far worse over Berlin than it had over Hamburg. The massive city appeared as an indistinct blob on radar displays. Identifying specific features or precise aiming points within that blob required interpretation skills that few navigators possessed. Berlin often lay hidden under cloud layers that persisted for days, eliminating any possibility of visual marking to supplement radar navigation. Flight Lieutenant Martin Weber flew 11 missions to Berlin between December 1943 and February 1944 as navigator aboard Lancaster N963. His experience with H2S evolved from initial confidence to growing frustration. Over Hamburg, the system had seemed like magic. Over Berlin, it felt like navigating by reading tea leaves. The radar display showed Berlin as a massive bright return covering the entire screen when set to 10-mile range. Weber was supposed to identify specific landmarks, the Tiergarten Park, the Spree River, government ministry buildings, armaments, factories. On the green cathode ray tube, everything blended together into an indistinct mass. He marked what he thought was the industrial district. Sometimes the bombing photography suggested he'd been close. Other times, evidence indicated his markers had fallen miles from intended targets. The psychological toll mounted alongside the strategic disappointment. Weber's crew understood they were bombing Berlin blindly, dropping tons of high explosive onto a city they could never visually identify, trusting that radar navigation placed them somewhere near military targets rather than purely residential neighborhoods. The moral calculus of strategic bombing had always been uncomfortable. At least when you could see the target, you knew what you were destroying. Bombing through radar felt like killing by remote control, launching ordnance at electronic ghosts that might represent factories or might represent apartment buildings full of civilians. The loss statistics told the strategic story Harris refused to acknowledge. Between November 1943 and March 1944, Bomber Command lost more than 500 aircraft over Berlin and related operations. That represented a loss rate of 5.8%, well above the 5% threshold that RAF planners considered the maximum sustainable casualty level. At these rates, Bomber Command would exhaust trained air crews before achieving decisive impact against Berlin's industrial capacity. The 16 raids killed approximately 4,000 German civilians, injured 10,000 more, rendered 450,000 homeless. But German war production actually increased during the same period. Berlin's industries, dispersed across the massive metropolitan area, proved far more difficult to destroy through area bombing than compact port cities like Hamburg. Harris had believed concentrated attacks on the capital would break German resistance. Instead, Berlin absorbed punishment while German fighter defences systematically destroyed British bomber formations. On the night of March 30th, 1944, Bomber Command launched its final major raid of the Berlin campaign, attacking Nuremberg with 795 aircraft. 94 were shot down, 71 damaged. The loss rate exceeded 12%, the worst single night of the entire war for Bomber Command. German night fighters, guided by their own increasingly sophisticated radar systems and aided by perfect moonlight conditions, had achieved a massacre. The Battle of Berlin ended not with German surrender, but with British operational exhaustion. Bomber Command couldn't sustain casualty rates that destroyed entire squadrons during single missions. Harris's prediction that 400 to 500 aircraft losses would cost Germany the war proved tragically inaccurate. 500 aircraft had been lost. Germany continued fighting. H2S hadn't failed through technical inadequacy. The system worked exactly as designed, providing radar navigation through weather conditions that would have made operations impossible using conventional methods. What H2S couldn't overcome was the fundamental limitation of its own resolution. The original Mark II system operated at 9.1 cm wavelength, producing radar images too coarse for precision targeting over large cities. TRE engineers had recognized this limitation even before the Battle of Berlin began. In September 1943, they initiated development of the H2S Mark III, operating at 3 cm wavelength with 10 GHz frequency. The shorter wavelength would provide 3 times better angular resolution, transforming the indistinct blob that Berlin appeared as on Mark II displays into recognizable features showing individual districts, parks, and major buildings. The Mark III entered operational service on December 2, 1943, during one of the Berlin raids. Aircraft equipped with the upgraded system reported dramatically improved target identification capability. Berlin's lakes and rivers appeared clearly defined. The Tiergarten showed as a dark area distinct from surrounding urban development. Major rail yards and industrial facilities generated characteristic radar signatures that trained operators could recognize. But production of Mark III equipment proceeded slowly. Most Bomber Command aircraft continued using Mark II systems throughout the Battle of Berlin. By the time sufficient Mark III sets became available for general deployment, the strategic focus had shifted. The Normandy invasion required Bomber Command to support tactical operations against French and Belgian targets. The campaign against German cities diminished in priority. The American equivalent, designated H2X and nicknamed the Mickey set, entered service in November 1943. Operating at the same 3 cm wavelength as British Mark III, the American system provided even higher resolution than the original H2S. More significantly, the 10 GHz frequency meant German Naxos detectors, specifically designed to intercept Mark II transmissions at 3 GHz, couldn't detect H2X at all. American bombers using Mickey sets remained electronically invisible to the German countermeasures that had been developed specifically to exploit British H2S vulnerabilities. The irony was profound. Britain had developed the world's first airborne ground-scanning radar, deployed it operationally before any other nation, achieved revolutionary improvements in bombing, navigation, and accuracy. Yet German capture of H2S equipment in February 1943 had triggered a technological arms race that Britain struggled to win. German scientists, given a functional example of cavity magnetron technology, immediately began developing their own centimetric radar systems and, more dangerously, detection equipment to exploit H2S transmissions. British bombers were simultaneously protected and endangered by the same technology. Protected because H2S enabled navigation through conditions that would otherwise ground the bomber force. Endangered because every transmission potentially revealed their positions to German night fighters equipped with Naxos receivers. The strategic calculation ultimately favored continued H2S use. Statistical analysis demonstrated that bombing accuracy improvements outweighed increased vulnerability to German interception. But individual aircrews experienced the technology's double edge more intimately than operational research analysts recognized. Flight Sergeant Michael Brennan, wireless operator aboard Lancaster P-372, flew his 29th mission on February 19, 1944, targeting Leipzig. His aircraft carried both H2S Mark II for navigation and Monica tail warning radar for detecting approaching fighters. The mission profile called for deep penetration into central Germany, 800 kilometers from English bases, through weather that would keep them in solid cloud most of the route. The H2S performed perfectly during the outbound flight. Navigator used coastal features to verify their position crossing the Dutch coast. Continued using radar returns to maintain accurate headings across Germany despite zero visibility. Identified Leipzig through complete overcast and marked the time for their bomb run. Then, 40 kilometers west of the target, Monica detected a contact closing from directly astern. German night fighter, almost certainly guided to their position by detecting H2S transmissions. The Lancasters gunners never saw the attacker. The Messerschmitt opened fire from below, where Monica couldn't detect targets, and the tail gunner couldn't depress his weapons sufficiently to return fire. Cannon shells ripped through P-372's fuselage, killing the flight engineer instantly and setting the port inner engine ablaze. Brennan barely escaped the disintegrating aircraft, parachuting into German territory where he spent the remainder of the war as a prisoner. During interrogation, German intelligence officers asked specific questions about British radar equipment. What frequency did H2S operate at? How many aircraft in a typical bomber stream carried the system? Had Monica been replaced by a different tail warning radar? The questions revealed how thoroughly Germany understood British electronic warfare capabilities. By July 1944, when a Junkers Ju-88 night fighter accidentally landed at RAF Woodbridge, allowing British intelligence to examine German equipment, including the Flensburg radar detector and Liechtenstein SN2 radar. The full scope of the electronic warfare battle became clear. German fighters had been homing in on Monica transmissions, using British-owned tail-warning radar to guide attacks against individual bombers. Naxos provided general location of the bomber stream by detecting H2S. Flensburg enabled precision attacks against specific aircraft by detecting Monica. RAF response was immediate. Monica was ordered turned off or removed from all aircraft. H2S, after intensive debate, remained in operation because its navigation benefits proved more valuable than the vulnerability its transmissions created. The Mark III version, operating at wavelengths Naxos couldn't detect, was prioritized for widest possible deployment. The technological seesaw continued through war's end. British engineers developed new systems. German scientists created countermeasures. American variants operating at different frequencies complicated German defensive calculations. Neither side achieved permanent advantage. Both sides learned that electronic warfare created vulnerabilities, even as it provided capabilities. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The weight of knowing too much pressed down on Oberleutnant Heinz Struning as he climbed into the cockpit of his Messerschmitt 210 night fighter on the evening of March 22, 1944. Above his canopy, a teardrop-shaped fairing housed the Fugue 350 Naxos Z radar detector, equipment so new that only 12 German night fighters carried it operationally. Struning had received exactly 2 hours of training on the system's use before his first operational sortie 3 weeks earlier. The device worked by detecting electromagnetic emissions from British H2S radar systems at ranges up to 35 kilometers. When RAF bombers transmitted their navigation radar signals, Naxos would pick up the emissions and display their approximate direction on a small cathode ray tube mounted beside Struning's instrument panel. The technology should have provided decisive advantage. German night fighters could locate the bomber stream without relying on ground radar guidance that British window jamming had rendered nearly useless. But Struning had learned through bitter experience that Naxos created as many problems as it solved. The device couldn't distinguish individual bombers, only the general location of the bomber stream. It provided no range information, no altitude data, no indication of how many aircraft were transmitting. The display showed a fuzzy blob indicating that British radars were operating somewhere in a particular direction. Finding a specific bomber within that electronic haystack required traditional methods, visual search aided by the same unreliable Liechtenstein radar that British jamming had degraded months earlier. Worse, Struning suspected that British intelligence knew about Naxos. RAF bombers had begun adopting erratic tactics during their bombing runs. Some aircraft would suddenly cease H2S transmissions for extended periods. Others would activate their radar only for brief navigation checks before shutting down. And again, the patterns suggested deliberate countermeasures designed to confuse German night fighters relying on Naxos guidance. Tonight's mission would target a bomber formation approaching Berlin. Ground controllers had detected approximately 600 aircraft crossing the Dutch coast at 8,000 meters altitude. The raid followed patterns established during months of sustained attacks on the German capital. Pathfinder aircraft equipped with H2S would mark the target. The main force would bomb the markers. German night fighters would attempt interception despite window jamming and despite British bomber tactics that made such interceptions increasingly difficult. Struning's Naxos receiver activated automatically during climb-out, its antenna rotating at 1,300 revolutions per minute to scan for British radar emissions. At 23 minutes past 11, the detector registered its first contact. A bearing indicator showed British transmissions coming from the northwest, exactly where ground controllers reported the bomber stream. Struning adjusted his heading and throttled up to maximum continuous power. The next 40 minutes demonstrated every limitation that Naxos possessed. Struning flew toward the indicated bearing, but the signal's strength remained frustratingly constant. He was getting no closer, despite flying at over 500 kilometers per hour. Either the bombers were flying away from him at nearly identical speed, or Naxos was detecting transmissions from aircraft so distant that his high-speed pursuit made negligible difference to the relative geometry. At midnight, Struning finally achieved visual contact, a Lancaster silhouetted against moonlight, flying straight and level at what appeared to be 7,000 meters altitude. The bomber was not transmitting. Either its H2S system was shut down, or Struning had found one of the bombers not equipped with the device. Traditional air combat protocols took over. Struning positioned his Messerschmitt below and behind the Lancaster, aiming for the blind spot where neither tail gunner nor dorsal gunner could engage him effectively. His cannon fire struck the Lancaster's port wing route, severing fuel lines and setting the inner engine ablaze. The bomber spiraled earthward, trailing flames, its crew abandoning the aircraft through emergency exits. Struning claimed the victory, his 19th confirmed kill, but professional satisfaction mixed with growing doubt about German defensive effectiveness. One bomber destroyed required 40 minutes of flying, consumed nearly half his fuel capacity, and succeeded primarily through luck rather than systematic tactical advantage. Naxos had guided him to the general vicinity of the bomber stream, but provided no help in actually locating individual targets. Traditional visual search and favorable moonlight conditions made the kill possible, not revolutionary radar detection technology. Similar frustrations plagued the hundreds of other German night fighter crews operating that evening. Naxos-equipped aircraft reported detecting British bomber formations but struggled to convert that general awareness into specific interceptions. Window jamming continued degrading conventional radar systems. The combination of British electronic warfare capabilities and improved navigation radar meant German night defences were gradually losing tactical effectiveness despite deploying countermeasures specifically designed to exploit British radar transmissions. The strategic implications extended far beyond individual combat encounters. German fighter production exceeded replacement rates, but trained pilot casualties were mounting faster than flight schools graduated new aviators. Each night's operations consumed resources, burned fuel, and killed experienced airmen at rates that made ultimate German defeat mathematically inevitable, regardless of tactical innovations like Naxos. Flying Officer James Maxwell studied the H2S display aboard Lancaster R for Robert as his pilot guided them toward Berlin on the night of March 24, 1944. 24 years old, Manchester native, university physics degree completed months before the war started. Maxwell had volunteered for Bomber Command specifically because they needed navigators with technical training capable of operating the revolutionary radar systems entering service. His 15 missions flying with H2S Mark II had taught him both the system's capabilities and its severe limitations. Over coastal targets like Hamburg, the radar worked brilliantly. Over inland cities without distinctive geographical features, the technology struggled. Berlin presented particular challenges. The massive city appeared as an indistinct bright return covering his entire display when set to normal range settings. Identifying specific landmarks within that electronic blob required interpretation skills that bordered on guesswork. Tonight's mission marked Maxwell's first operation using the newly installed H2S Mark III system. The upgraded equipment operated at 3 cm wavelength instead of the 9.1 cm wavelength used by Mark II. The shorter wavelength provided 3 times better angular resolution, theoretically transforming the indistinct Berlin blob into recognizable features showing individual districts, parks, and major buildings. Maxwell activated the Mark III system as they crossed the German coast. The improvement was immediately obvious. Where Mark II had shown Hamburg as a general bright area, Mark III displayed the city with remarkable detail. He could distinguish the harbour installations, the river channels, even individual clusters of buildings that represented major industrial facilities. If the technology worked this well over Hamburg, Berlin might finally become a practical target for precision radar bombing. The bomber stream proceeded inland through complete overcast that persisted from ground level to over 3,000 meters altitude. Visual navigation remained impossible. Traditional dead reckoning would have left them guessing about their exact position within margins of error exceeding 10 kilometers. H2S Mark III provided continuous position updates by comparing radar returns against known geographical features. Maxwell tracked their progress across northern Germany by identifying towns, lakes, and rivers that appeared distinctly on his display. Each landmark confirmed their heading accuracy. By the time they approached Berlin's outskirts, he had accumulated sufficient confidence in the system to provide precise timing estimates for their bomb run. Berlin appeared on the Mark III display at 70 kilometers range, far exceeding the Mark II's useful detection distance. More significantly, the city showed structure rather than formless brightness. Maxwell could distinguish the Tiergarten Park as a dark area distinct from surrounding urban development. The Spree River appeared as a dark line winding through the bright returns of dense construction. Major rail yards generated characteristic patterns that he recognized from intelligence photographs studied during pre-flight briefing. The improved resolution transformed H2S from marginal navigation aid into genuine targeting system. Maxwell identified the industrial district selected as their aiming point, marked the moment for bomb release, watched their payload fall away toward a target he could track electronically, but had never seen with his eyes. For the first time in 16 missions over Germany, he felt confident they had actually bombed what they intended to bomb, rather than dropping ordnance blindly into darkness and hoping for favorable results. The psychological transformation proved as significant as the tactical improvement. Precision radar bombing felt different from area bombing conducted by estimating positions and hoping for the best. Maxwell wasn't murdering German civilians indiscriminately. He was destroying specific military targets using the most accurate technology available under conditions where visual bombing remained impossible. The moral calculus of strategic bombing had never been comfortable. At least Mark III allowed him to believe his bombs struck military rather than purely residential targets. Similar experiences among other Pathfinder crews flying Mark III-equipped aircraft that night suggested the upgraded system represented genuine technological advancement. Post-raid photography would later confirm that bombing accuracy had improved dramatically compared to previous Berlin raids conducted using Mark II radar. The concentration of damage around intended aiming points exceeded anything achieved during the months of the Battle of Berlin. But production limitations meant Mark III remained rare. Most Bomber Command aircraft continued using Mark II systems throughout spring 1944. The technology that could have made the Berlin campaign strategically effective arrived too late to change the outcome. By the time sufficient Mark III sets became available for general deployment, strategic priorities had shifted. D-Day preparations required Bomber Command to support tactical operations against transportation networks in France rather than continuing strategic attacks against German cities. The bitter irony haunted Bernard Lovell long after the war ended. His H2S concept had been proven correct. Ground-scanning radar could guide bombers through complete overcast to bomb targets with unprecedented accuracy. But institutional inertia, production delays, and the catastrophic June 7, 1942 crash had prevented the technology from achieving its full potential when it mattered most strategically. The Mark II system deployed during the Battle of Berlin lacked sufficient resolution for precision targeting over large cities. The Mark III system that solved those resolution problems entered service months too late to affect the strategic bombing campaign's outcome. British and American bombers had killed hundreds of thousands of German and Japanese civilians, while Lovell's improved radar system sat in development, delayed by manufacturing challenges and bureaucratic caution. Lovell would spend decades after the war grappling with the moral implications of his work. H2S had saved thousands of Allied airmen by enabling navigation through weather conditions that would have made operations impossible using conventional methods. Those same systems had facilitated area bombing campaigns that killed civilians with industrial efficiency. The technology itself carried no moral character. Its ethical implications derived entirely from how military commanders chose to employ it. The German response to H2S demonstrated both the Wehrmacht's technical competence and its ultimate inability to overcome Allied material superiority. Telefunken engineers, given a captured H2S system in February 1943, had reverse-engineered the technology with impressive speed. Naxos radar detectors entered operational service by September. Barely 7 months after the Rotterdam crash provided German scientists with their first cavity magnetron. But knowing British capabilities and developing effective countermeasures proved to be two entirely different challenges. Naxos could detect H2S transmissions but couldn't provide the precision guidance necessary for effective night fighter interceptions. German night fighter effectiveness declined throughout 1943 and 1944, despite deploying detection equipment specifically designed to exploit British radar emissions. Window jamming, improved RAF tactics, and the sheer scale of Allied bomber formations overwhelmed German defences regardless of technological sophistication. The final German countermeasure arrived too late to matter. Telefunken had developed a 3-centimetre version of Naxos-designated ZX, capable of detecting Mark III and American H2X transmissions. Production commenced in early 1945, But Allied advances overran the manufacturing facilities before meaningful quantities entered service. Even if German factories had produced thousands of Naxos ZX sets, the Luftwaffe lacked sufficient fuel, trained pilots, and operational aircraft to mount effective bomber interception campaigns. Unteroffizier Klaus Weber, the radar operator who had watched his Würzburg station's displays dissolve into electronic chaos during the Hamburg window attacks, survived the war and returned to civilian life, haunted by memories of technological obsolescence. His professional expertise in radar operation had become militarily irrelevant within months of British countermeasures deployment. The skills that had made him valuable to German air defence in 1942 meant nothing by 1944, when window jamming and British radar superiority rendered German ground control nearly useless. Weber would later write in private correspondence that the war's outcome had been determined not by courage or tactical brilliance, but by electromagnetic physics applied through superior industrial capacity. Germany possessed brilliant scientists and competent engineers. German forces fought with discipline and determination. None of that mattered when British physicists developed better radar systems and British factories produced them in quantities that overwhelmed German countermeasures. The H2S story encapsulated that larger strategic reality. Britain had conceived, developed, and deployed airborne ground scanning radar, while Germany struggled to produce even basic countermeasures. American industrial capacity amplified British technological advantages by mass-producing improved systems faster than German engineers could devise responses. The war became a contest of industrial physics, where Allied material superiority eventually crushed German resistance through sheer accumulation of technological capabilities that the Wehrmacht couldn't match. Flight Sergeant Thomas McKenna, the navigator who had operated H2S during its first operational deployment over Hamburg, completed his tour of 30 missions in July 1943. He returned to civilian life, carrying memories of electronic navigation through darkness and clouds, of marking targets he could never see visually, of watching cathode ray tubes display ghostly green representations of cities burning beneath his bomber. McKenna had witnessed the transformation of aerial warfare from visual combat to electromagnetic operations conducted beyond human sensory perception. His generation had fought the First War, where electronic systems determined tactical outcomes independent of traditional military skills like marksmanship, navigation by stars, or reading terrain features. Radar operators interpreted electronic signals that represented reality rather than experiencing that reality directly. The psychological distance inherent in radar bombing made killing easier and guilt harder to process. In his final years, McKenna would tell anyone who asked that H2S represented humanity's first step toward push-button warfare conducted at distances that eliminated personal connection between attackers and victims. The technology enabled military operations that would have been impossible using earlier methods. It also enabled mass destruction of civilian populations with industrial efficiency that earlier warfare could never achieve. Whether that represented progress or moral catastrophe remained a question McKenna never resolved to his own satisfaction. The strategic bombing campaign's legacy remained bitterly contested long after the war ended. Bomber Harris maintained until his death that area bombing had been necessary to destroy German military capacity and shorten the war. Critics argued that indiscriminate attacks on civilian populations constituted war crimes regardless of military necessity. Post-war analysis suggested that strategic bombing achieved mixed results at enormous cost in lives and resources. H2S technology itself couldn't answer those moral questions. The radar system worked exactly as designed, providing ground mapping capability that enabled navigation and target finding under conditions where visual bombing remained impossible. Whether military commanders should have used that capability to conduct area bombing campaigns against civilian populations involved ethical judgments that transcended technical considerations. What remained indisputable was the technology's revolutionary impact on warfare. H2S and its American counterpart H2X demonstrated that radar could guide weapons to targets beyond visual range or through complete obscuration. That fundamental principle would shape military technology development throughout the Cold War and into the 21st century. Precision-guided munitions, synthetic aperture radar, GPS navigation systems, all descended conceptually from Lovell's wartime work on airborne ground scanning radar. The cavity magnetron that powered H2S survived the war to enable peacetime applications ranging from microwave ovens to cellular telephone networks. The rotating antenna mechanisms developed for radar bombing evolved into airport weather radar systems. The cathode ray tube displays that showed ghostly green images of European cities became precursors to modern computer monitors. Technologies developed for nighttime destruction found new purposes in post-war civilian applications. Bernard Lovell himself abandoned military radar work immediately after VE Day, returning to his first love of radio astronomy. Using surplus military radar equipment, he built the Jodrell Bank Observatory, pioneering the use of radio telescopes to study cosmic phenomena. The same technical expertise that had enabled bombing through clouds allowed him to detect radio emissions from distant galaxies. His post-war career demonstrated that electromagnetic theory could serve knowledge and discovery as effectively as it had served destruction. The H2S story ended not with dramatic victory or catastrophic defeat, but with the quiet obsolescence that eventually claims all military technology. By 1950, jet aircraft and atomic weapons had rendered World War II-era radar systems outdated. The cavity magnetrons that once represented cutting-edge technology became museum pieces. The navigators who had learned to interpret fuzzy green radar displays retired from service as newer systems replaced the equipment they had mastered. But the fundamental principle remained valid. Understanding how enemies perceive their environment, then systematically degrading that perception, represents a form of victory more subtle than destroying physical forces, but often more decisive strategically. The British had developed radar systems that allowed them to see through darkness and clouds. The Germans had developed countermeasures that detected British radar transmissions. The British had responded with improved systems operating at wavelengths German detectors couldn't intercept. The cycle of innovation and counter-innovation had continued until material exhaustion ended Germany's ability to compete technologically. The lesson transcended specific technologies or particular wars. Modern military forces that controlled electromagnetic spectrum would dominate opponents who relied on outdated systems. The nation that fielded better sensors, more sophisticated jamming equipment, and more resilient communications would defeat adversaries regardless of traditional military advantages in numbers or fighting spirit. World War II had demonstrated that industrial societies fought by manipulating physical laws rather than through personal valor or tactical brilliance. Klaus Weber, the German radar operator who had watched British electronic warfare systematically destroy his station's effectiveness, survived into his 80s. In final interviews conducted before his death in 1997, he reflected on how completely electronic technology had reshaped warfare during his lifetime. The Würzburg radar that had seemed invincible in 1942 had been neutralized by British countermeasures within 18 months. The technological supremacy that German forces had enjoyed early in the war dissolved when Allied scientists developed superior systems and Allied factories produced them in overwhelming quantities. Weber's experience encapsulated broader truths about technological warfare. Temporary advantages gained through innovation disappeared when opponents developed countermeasures or superior technologies. The arms race between offensive capabilities and defensive responses accelerated constantly, consuming resources while providing diminishing strategic returns. Nations that couldn't match their enemies' innovation rates eventually lost regardless of other military capabilities. The electromagnetic spectrum had become a battlefield as contested as land, sea, or air. Control of that invisible domain determined who could navigate accurately, who could communicate reliably, who could detect enemy forces before being detected themselves. World War II marked humanity's first experience with warfare, where success depended as much on physics and engineering as on courage and tactics. H2S represented one chapter in that larger story of technology reshaping military conflict. James Maxwell, the young navigator who had operated Mark III radar during the final months of the European War, returned to civilian life and eventually pursued graduate studies in electrical engineering. His wartime experience with cutting-edge radar systems gave him advantages over classmates who had no exposure to microwave technology. Maxwell would later become a professor, teaching post-war generations about electromagnetic theory that his students couldn't appreciate without understanding how that theory had enabled precision bombing through complete overcast. In lectures delivered during the 1960s, Maxwell would tell students about flying through darkness above Berlin, with nothing but a green cathode ray tube, showing him where to release his bombs. The younger generation found such stories almost incomprehensible. They had grown up with television, radar speed traps, and weather forecasting based on Doppler radar. The technology that had seemed revolutionary in 1943 had become commonplace consumer electronics by 1965. That rapid transformation from military secret to civilian commodity demonstrated how completely electromagnetic technology had permeated modern life. The same physical principles that enabled H2S radar-guided commercial aircraft through fog. The same cavity magnetrons that powered bombing radar heated food in millions of kitchens. Technologies developed for destroying enemies found peaceful applications that dwarfed their original military purposes in economic and social significance. Bernard Lovell received a knighthood in 1961 for his contributions to radio astronomy, with no public mention of his wartime radar development work that remained classified for decades after the war ended. He lived to age 98, dying in 2012, having witnessed both the destructive applications of his radar innovations and their peaceful evolution into technologies that benefited humanity. In his final autobiography, Lovell wrote that he remained troubled by memories of bombers guided by his equipment killing civilians, but took solace in knowing that the same technical knowledge had enabled scientific discoveries about the universe's structure and origin. The H2S radar system, designated a historical treasure by Britain's Science Museum, sits, preserved behind glass, its rotating antenna and cathode ray tube display unchanged from 1943 configuration. Museum visitors who examine the equipment rarely comprehend how revolutionary the technology seemed to crews who first operated it over Hamburg. The green displays that showed city maps through complete darkness represented capabilities that bordered on magic by wartime standards. That rapid shift from revolutionary to historical to obsolete defined every aspect of World War II technological development. Innovations that required years of desperate effort to develop became outdated within months, as newer systems replaced them. The war accelerated technological progress by compressing development timelines through unlimited funding and relaxed safety requirements. Peacetime research that might have required decades occurred in compressed timeframes, measured in months when survival depended on achieving technical superiority. The final assessment of H2S effectiveness remained complex and contested. The system had enabled Bomber Command to continue operations through weather conditions that would have grounded the force using conventional navigation methods. It had improved bombing accuracy over coastal targets with distinctive geographical features. It had saved thousands of aircrew lives by reducing dependence on visual navigation that required descending below clouds into concentrated flak zones. But H2S had also facilitated area bombing campaigns that killed hundreds of thousands of civilians while achieving debatable military results. The technology's capabilities exceeded its limitations, primarily over targets like Hamburg, where geography favored radar identification. Over inland cities like Berlin, even the improved Mark III system struggled to provide the precision necessary for attacking specific military installations rather than general urban areas. The strategic question remained whether developing H2S represented wise allocation of Britain's limited scientific and industrial resources. Alternative technologies might have provided greater military benefit at lower cost. More sophisticated radio navigation systems like oboe achieved better bombing accuracy but suffered range limitations. Improved bomb sights for visual bombing worked brilliantly in clear weather but proved useless under overcast. H2S represented compromised technology that worked adequately under most conditions without excelling in any specific scenario. German forces never developed comparable airborne ground scanning radar, despite capturing H2S equipment and reverse engineering its operating principles. Telefunken engineers built experimental systems based on the Rotterdam Gerät, but production never reached meaningful scales before Allied victories ended German technological development. The cavity magnetron technology that enabled British 9cm radar required manufacturing capabilities that German industry couldn't replicate under wartime conditions. That failure reflected broader German strategic miscalculations about technology development. Reich leadership had ordered research centers to abandon projects unlikely to produce results within 6 months, assuming the war would end quickly. British scientists, operating under no such constraints, pursued long-term research that eventually yielded decisive advantages. The cavity magnetron development took years. H2S system integration required months of testing. German unwillingness to invest in extended research programs meant they fell permanently behind in critical technologies. The electromagnetic warfare lessons learned during World War II shaped Cold War military development for decades afterward. Both superpowers invested enormous resources in radar systems, electronic countermeasures, and signals intelligence capabilities. The realization that controlling the electromagnetic spectrum provided decisive military advantages drove the technological competition that eventually produced satellite navigation, stealth aircraft, and precision-guided munitions capable of striking targets in any weather, any darkness, through any obscuration. H2S represented the first operational step toward that future of push-button warfare, conducted at distances that eliminated human connection between attackers and victims. The technology that enabled night bombing through clouds in 1943 evolved into cruise missiles, striking targets thousands of kilometers away, guided by satellite navigation systems that descendants of Lovell's wartime radar work made possible. Whether humanity benefited from that technological evolution remained a question that each generation answered differently based on their experiences with modern warfare's increasingly remote and sanitized violence.